Last time we showed the first experiments that produced negatively charged particles. This time we're going to see how J.J. Thomson cleverly arranged an electric and magnetic field in order to measure the charge-to-mass ratio of these new particles. To get started, let's say our beam of particles is coming in from the left and is traveling in a straight line as shown in the last video with some unknown velocity v. In the presence of a magnetic field pointed into the board, the negatively charged particles are going to experience a force in the down direction equal to Q times V times B, where Q is the unknown charge of these particles, V is the unknown velocity, and B is the magnetic field strength. So what would happen if this beam of particles was exposed to just this type of magnetic field is that they would bend down in response to this force. However, we can apply an electric field perpendicular to both the velocity and the magnetic field in order to balance out the electric force. The electric force felt by these particles is going to be Q times E. With Q still being unknown. However, if we equate these two forces, we see that the charge of these particles becomes irrelevant. And all that's left is that the velocity v is equal to E over B. What this means experimentally is that if you have a beam of unknown charged particles moving at an unknown velocity, you can turn the knobs of your electric and magnetic fields until you observe the beam doesn't bend in any direction and just continues forward in a straight line. And at that point, you can be sure that all those particles are going at exactly the speed v is equal to E over B, given by the knobs you turned. In this way, J.J. Thomson measured the exact velocity of the particle beams he was studying. Later in this beam's journey, we can make it encounter a known electric field. In this electric field, the beam will feel a constant force equal to QE again, and will therefore undergo uniform acceleration and follow a parabolic path identical to a ball being thrown in a gravitational field. By knowing exactly how long the electric field region is, and measuring exactly how far the beam bent, we can write an expression we solve to get the charge-to-mass ratio of these particles. First of all, x equals v times t, where v is the velocity of the particles times the time in the field region. Since we know v from before, we can calculate the time these particles are uniformly accelerated for. Once we know the time, we can write an expression for the distance the beam bends as y equals 1/2 at squared, where the acceleration is given from F equals ma, is equal to the force QE. And since A is equal to E, which we know, times Q over m, once we measure the acceleration in this way, we know the charge-to-mass ratio of these new particles. And this is exactly what J.J. Thomson got the Nobel Prize for, because after he did this experiment and found that these new particles were 2,000 times less massive than the lightest known atom, that of hydrogen, and so could no longer be the building block of everything as previously thought. since we just found something smaller than an atom. These new particles, as you probably know, are the electrons.